Hello, welcome to my presentation on logistic regression. So for an introduction to logistic regression, it's important to look at linear regression first, because that measures relationships, predictions, and confounding effects. So it's essentially the relationships between predictors and an outcome, but in this case, logistic regression is built for more binary cases. So for instance, it's going to model how independent variables affect binary outcomes, such as survival or death. And it's essentially death would be 1 and survival is 0. So it's going to retain the linear regression model, but it differs in that it works with probabilities between 0 and 4. So an example in the textbooks was 30-day mortality rates for septic patients admitted through the emergency department using multiple patient and hospital factors. So to differentiate between linear and logistic regression, on the left we have linear regression, which assumes a straight line relationship that can predict continuous outcomes that are influenced by independent variables. So it works well when your outcome is continuous. So for instance, like GPA, height, or income. But when you try to use it for binary outcomes, like yes or no, it can give impossible predictions, like a probability of greater than, less than, or 0. So logistic regression on the right fixes that by transforming the equation. Instead of predicting a straight line, it predicts the log odds of the outcome. Basically, the log of the probability that something happens versus it doesn't. This means that this method is built for binary outcomes where 0 equals no and 1 equals yes. It converts those probabilities into log odds, keeping everything between 0 and 1. So, and it also uses the maximum likelihood estimation to find the best fitting model. Basically, it's going to choose the coefficients that make the observed outcomes the most probable. So, as you can see at the bottom, the formula changes from a simple linear equation to the one that includes the natural log of the odds. So instead of drawing a straight line, logistic regression will give us an S-shaped curve where the probabilities gradually level off near 0 and 1. So that's what makes logistic regressions so effective for predicting whether someone has a disease, passes classes, or renews a gym membership, anything with a yes or no outcome. So nice. So interpreting the coefficients as odds ratios. So once we have the coefficients, we convert them into odds ratios by exponentiating them. If and or is greater than 1, it means the variable increases by the odds of the outcome. Less than 1 means it's protective or reduces the odds. We can also include the 95% confidence intervals, which tells us the range we can be at 95% confident the true odds ratio lies in. So if an interval crosses 1, it is not statistically significant. So the importance of logistic regression, it's an important method in research and data analysis when we have binary outcomes. So first, it can handle multiple predictors at once, meaning we can look at the combined effect of several independent variables on a single binary outcome. So for example, if we're studying heart disease, we can include age, cholesterol, exercise habits, and blood pressure in all one model. Second, it can adjust for the confounding variable statistically. So a confounder is something that affects both the predictor and the outcome, like age influencing both smoking habits and the likelihood of a lung disease. So it allows for us to control those kinds of variables so we can isolate the true effect of what we're studying. So third, it works when randomization is not feasible, which makes it ideal for observational studies and real-world research where we can't always assign people to groups. So fourth, the model gives us interpretable probabilities, which is a huge decision making. Instead of saying something how is related, logistic regression tells us how likely an event is to happen, and that's much easier to communicate in applied fields like healthcare or business. And finally, it's key for evidence-based practice and research translation in fields like medicine, public health, and even social sciences. So logistic regression is one of the most trusted tools for turning raw data into meaningful, actionable evidence. So when selecting independent variables, it's emphasized that choices should come from theory and prior evidence, not just what is statistically significant. So we want predictors grounded in accepted research or clinical reasoning. Secondly, we need to include potential co-founders like age or socioeconomic status, even if they're not significant, because they help control bias and give a clear picture of what's really influencing the outcome. Next is univariate screening, where each variable is tested individually first, and Saalfeld suggested we using a relaxed cutoff of p less than 0.25 so we don't exclude something that could matter later in the model. It's also a key to watch for multicollinearity, meaning variables don't overlap too much, so something like weight and BMI, since those can distort coefficients. Finally, we want to keep the sample size balanced using the 10 to 20 events per rule variable and avoid overfitting by keeping the model simple and conceptually focused. So a smaller and well-adjusted model usually performs better and generalizes more reliably. So before we start building a logistic regression model, it's important that we make sure we have as few core assumptions that are met, and this is what's going to keep our model statistically valid and reliable. So the first one is independence of variables, where each observation is unique. And the data, one person's data can't influence another's, and that shouldn't include repeated measures on the same individual. So if we violate this, we can end up underestimating standard errors and inflating the significance of the results. Next, we have linearity in the logit. This is the one specific to logistic regression. It means that continuous variables should have a linear relationship with the log odds of the outcome and not necessarily the raw probability itself. And then we want to make sure there's no multicollinearity, where predictors shouldn't be too highly correlated with each other. When two variables measure nearly the same thing, like height or leg length, it becomes hard for the model to actually figure out which one could be the outcome. And the fourth obsession is there's no influential outliers. Outliers can pull the regression line or distort the coefficients, especially in smaller data sets. And finally, we want to have the sample size rule. So it's recommended that we at least have 10 to 20 outcome events per predictor variable. This helps prevent overfitting and keeps your estimates stable. So once we've selected our independent variables and confirmed the assumptions are met, the next step is deciding how to actually build the model. And so there's three main strategies for this. We have our direct standard, our hierarchical sequential, or our stepwise. So the direct standard is the default and the most straightforward, where you enter all your predictors into the model at once and interpret how each one contributes for controlling the others. This approach is common when you already have a strong theoretical foundation and you're confident in which variables belong in the model. The second is hierarchical or sequential entry, where you add variables in blocks or stages based on the theory or logic. This helps you see how each set of predictors improves the model and whether new variables meaningfully change the relationships you already found. Then we have our stepwise or statistical method. This one lets the computer automatically add or remove predictors based on statistical significance, like forward selection or backward elimination. However, stepwise may overfit or capitalize on chance correlations, but it's recommended that we always validate the model afterward, ideally a different data set or with cross-validation, to make sure it generalizes beyond your sample. Next, we're going to have internal versus external validation, and these are validation practices. So it really checks how reliable our model truly is. An internal validation tests whether the model replicates within the same data set using methods like cross-validation or bootstrapping, while external validation applies it to a new data set to see if it generalizes beyond the original data. So a well model performs both consistently across both, and then both types are going to be needed in order to have strong evidence. Right, so interpreting the model, we have an evaluation model of fit. So this evaluates how well it fits the data. This is where we look at few key measures that tells how accurate and reliable it is. So the first is a goodness of fit, and these are the chi-squared, residual deviance, and the Homer test, which helps us see how closely the model's predicted outcomes match observed outcomes. So smaller differences between what the model predicts and what actually happened means a better fit. The next piece is discrimination, which helps measures how well the measure can distinguish between two possible outcomes, like predicting who or who doesn't have a condition. So the metrics we can use are the AOC, or area under the curve. So an AUC of 0.5 means the model is no better than random guessing, while 1, it means perfect prediction. Lastly, we check the diagnostics, so things like residuals, leverage, and influence statistics, which help us identify outliers or data points that have a usually strong impact on the model. Now that we've confirmed the model fits the data well, we need to interpret the output, which is where we can make sense of what actually happens. So each independent variable is reported as the odds ratio, or with a 95% interval. So the odds ratio tells us how the odds of the outcome change for every 1 unit increase in that variable while keeping the other variables constant. So the confidence interval includes 1-0. That means the effect is not significantly significant. In other words, we can't be confident that the predictor truly influences the outcome. For example, if the odds ratio is 1.5 with a confidence interval of 0.85 to 2.3, that crosses 1. So it wouldn't be considered significant. But Stolfholz makes an important point that not to just focus on the statistical significance, and so we could look at whether the result is clinically or practically meaningful. So even a small effect might be worth paying attention to if it has a real-world impact. For instance, a small increase in risk could matter in public health or patient safety context. Finally, when we interpret the model, we want to look at all three things: direction, magnitude, and reliability itself. So interpreting the model output isn't about p-values, it's about how understanding the story of your model telling and whether it makes sense in a real-world context of your research.